Hmm. Why isn't this working? Oh, it is working. Okay, I'm going to wait till I hear my audio. Okay, it's working. Great. Sorry about that. All right. Welcome everyone to this EJA unboxing stream tonight, whether you're watching it live or recorded afterwards. So to give a bit of an overview of what this is all about, EJA is a project as a part of the Hackaday Dream Teams initiative. So it's a collaboration between myself, Leonardo Ward, and Toby. And what we have set out to develop is an open source ropeless fishing system. A ropeless fishing system is a device that's used in combination with lobster traps or crab pots, so that way the buoy can be released after a certain amount of time, or by a certain sort of sensor trigger or acoustic command. So basically, our robot gets thrown into the water to the sea floor along with these traps, and then after a certain period of time, it releases a buoy along with a vertical line that then goes to the surface. The reason why these ropeless fishing systems are needed is because, especially on the East Coast, there's a declining population of North Atlantic right whales. Currently, the estimated count is only 360 on the entire planet. These whales get entangled with the current method that's used for fishing, which is a lot of vertical lines to the surface buoys. So a device like this would be able to alleviate that problem. There's of course a lot more to it than that simple overview. So if you're interested in learning more about like the whole reason why this is a problem, there's a research report on our hackaday.io project page. I'll update the description to have that link as well. This is our second version of this robot. The first one was made last year, which took us through the whole process of determining which strategy to use for this ropeless gear robot, and we demonstrated the functionality. And then this summer, we've been working on refining this so that way it can be a product that we can produce more units of. So today's stream is covering the pieces that we have received finally after 3 months of development on this robot. So it's been 3 months of design, and now we finally get to see the pieces that have been fabricated. So we have 3 sets of pieces here. The sets of pieces, one set is from Design Lab in Pasadena, California, a part of Supply Frame and Hackaday. So a big thanks to them. The second set of pieces were fabricated here in Ontario. So thank you to Jason for fabricating these. This is great because it's also metal. And then the third set was fabricated in-house on a 3D printer. So there's a whole set of pieces here. So how this live stream is going to work is currently there's one viewer, which is probably myself. But if anyone is out there actually watching, free to submit or just chat on the chat box there, and I'll be able to read it out loud and see what people are saying. And if you have questions at all, then I can answer those questions and describe more about the pieces. I'll be talking a bit about each piece as I unbox it. So on the screen right now, on the left-hand side, sorry about this, there is an issue. Okay, sorry about that. YouTube said that there wasn't a good enough connection. However, that was not what I saw on my end. Anyway, we're back now. Okay, so how this stream is going to work, apart from technical difficulties, is I'll be describing a bit about each piece as I unbox it. As well, on the left-hand side of the screen, on the upper portion, you'll see that there's a piece of cardboard in high definition. It's a very nice looking piece of high definition cardboard. But that will be our place to put pieces close up. As well, there is a CAD view of the EJA assembly, so that way I can point out where these pieces are in the actual assembled robot. So with the high definition cardboard cam here, I can switch it to this view, so that way you can see the cardboard in high res. All right. I'll stop joking about that now. Okay, so there is one person here, apart from me, who's watching the stream. So Nerd Garage, thanks for tuning in. Yeah, huge crowd for sure. Let's see if we can handle it. Oh, nice. So Nerd Garage mentions about this show called Deadliest Catch, and they can see multiple ways where this could be useful. That's one of the nice ways about when we were designing the project is all the intelligence is in the buoy, so you can supplement that with additional sensors. And it has a magnetically coupled actuator, which can change depending on the purpose. So right now it's a wiper, but we could make the actuator into a flipper or an agitator, food release, which would be great for bait. So yeah, thank you for that. And apparently the stream has been good here the whole time. Great. Yeah, I don't know why YouTube showed that error message. All right, so I'm going to go ahead and oh wait, I actually don't have access to a keyboard right now, so I can't tweet anything and I can't reply in the chat. So we'll just proceed with unboxing the pieces then. All right, so here we go. Okay, here's the first piece. This is a handle. I'll remove that piece. This is a handle. This is the deck. The deck is what's used to help transport the robot. As you can see in the CAD, it's sort of a robot that has these stands. So those stands fit in here. And then you can hold the robot and bring it onto your ship or your boat or whatever using this deck. Great. And it's very nicely smooth, sanded, which makes it great to be able to hold without getting splinters. So let's see here. I'll put the engraving up on here so you can see. Okay. So we've done the handle. Now, next up are the base pieces. So the base pieces, the robot's comprised of two stages, the lower stage and the upper stage. Here's the lower stage. So with the lower stage, we have access to all of these mounting holes or mounting points. And this is the one that will probably be entering the water first. Then for the upper stage, we have this piece. This is the piece where the buoy, in this case we're using a Nalgene water bottle, rests. So this, which is the Nalgene, rests on here with some additional pieces. So this is made out of HDPE, and actually it looks like it's the same piece of material that we used last year. So this was last year's base, so quite a bit different. But I believe this was 3/8 inches. Yeah. And so this was cut out of that. And what's great is that you can tell that the size of the robot is much more compact this time in terms of surface area, which affects the force of drag. However, it will be a little bit taller. Okay, so that takes care of those two pieces. And the bases have also been fabricated in aluminum. This is 1/8 inch aluminum, 60/60. Yeah, it was fabricated on a water jet cutter, so that means all of the cutouts are very nice, meaning without distortion. In terms of mass, it's tricky to compare. I would say they would actually be quite close in mass, which is interesting because this takes up more volume than this. Volume affects buoyancy. So that's something important to keep in mind. Here's the other handle. So on the CAD model, you can see the handle. The handle attached to the upper stage base, and the idea with an asterisk there is that the handles will be the pieces where like this is grabbed onto by the fishers to bring it on board, or it's held here to throw it overboard. We'll see how well this works with these handles. So the handles look like they have been sliced in half of the 3/8-inch piece. We had flexibility on the height of the handles because it is at the upper portion of the upper stage of the threaded rods. So that gave us some flexibility in terms of material height. We could have used from 1/8-inch, I think, all the way up to 1/2 inch even. So we'll be able to see how well this smaller thickness holds up, and then go from there. Okay. So the biggest, I guess, bunch of pieces here is this bag. So this bag holds the stand pieces, and I mentioned before about the stands that they fit into here, and yes, it is true that the stands do fit. So, haha, can't hardly see it, right? Oh, still can't hardly see it. There we go. So something interesting about these stand pieces, they are 3D printed, sort of needed that for the geometry, and they are in a material of nylon. So I also 3D printed some of these in-house. Here you can see the blue ones, and the mast is significantly different. The black piece, or the nylon piece, weighs quite a bit more than the blue piece. I'll be able to get some quantitative numbers on this later, but it's just fascinating to see, really. So that's pretty awesome. All right, next pieces. So these pieces are spool holders. The spool is what the rope is on. So here you can see we have a spool of paracord. This is 100 feet or 30 meters of paracord. And I am uncertain that this was the revision with the increased depth. Anyway, okay. So these pieces, did I make a mistake? I believe I have made an error. The first error. Nope, no error. It's all good. Okay. Okay, there is a copy of the improved revision. Okay, so these spool holders are to hold the spool for the vertical line of the buoy from the base. So here is what has been created on the 3D printer here. So I basically sort of printed a portion of the base, the lower stage, and then printed the spool holders. So there will be a rod in between. hold the spool. And then here is the nylon 3D printed piece, which is just awesome. It is much more sturdy as well. Same thing with the stands. The mass is considerably more. So the part that I was debating about before was the thickness of this portion. This increased from 3 millimeters, I believe, to 5 millimeters in the final revision. That's also what is printed here. So the other two in this stack are that same 5 millimeters. So that's good news. Put that over there. All right, next up for the pieces. Okay, we will unbox this one next. And yeah, big thanks to Design Lab for doing such an awesome job. Same as this Jason, an awesome job with these pieces. Okay, here we have the GoPro holders. These were 3D printed such that their orientation was this way going up, so that way you wouldn't have your GoPro snapping. So yeah, this is great. It's pretty sturdy for a 3D printed GoPro holder piece. Next piece. So this piece in my hands here is the cap. So the cap is what attaches onto the external wiper and sort of completes the assembly. So in my hand here, I have the external wiper, and then the cap just sort of sits on top like that. This next piece that is in the same bag is the external magnet holder. Now this is a piece that we're actually going to end up fabricating here. And the reason why is because the alignment of the magnets will be checked, has to be checked manually, like once it's built in person. So that piece fits into the external wiper, and then the cap goes on top of it, sort of like that, and then it ties it all together. Okay, next up is this piece. This piece is the handle of the buoy. So this one was also fabricated in HDPE. And this serves as the mounting point for rope to attach to the buoy. As well, these two holes, that is where it attaches to the clamps that clamp onto the buoy. All right, next up is this piece. Wow, cool. So this piece is the external wiper as well. So this one we also fabricated here. And this external wiper that was fabricated at Design Lab, it's also nylon filament. And it's so difficult to describe this, but the mass is so much more. Yeah, it's going to be really neat to like test these and also compare. So what's interesting about the external wiper piece is that the design has a slight ridge on the two ends, and that ridge is such that the only area that is touching the external face of the buoy or the Nalgene water bottle is those two ridges. I will move it to the close-up camera. So these two ridges right there. And the reason why this is to reduce the amount of friction that is between the external wiper and the buoy. As well, there's an additional reason, and that's because we want to reduce scratches on the polycarbonate. So this is the external wiper, and then as mentioned before, here's the magnet holder, and that goes in there, and then the cap goes on like that. Now for this piece, the magnet holder will actually have the magnet sort of exposed because the magnets get inserted this direction. So that means that for this version of the external wiper, it won't necessarily work because this wall needs to be completed. Now, most likely what happened is that in the slicer settings, because it detected a very thin wall on the scale of either 0.6 millimeters or 0.8 millimeters, it likely did not complete the wall, and that's why it is missing there. Here you can see a comparison. This one over here has the 0.8 millimeter wall completed. This is fine though, because I believe there is another external wiper piece, so I'm not overly concerned about that at this point. So, speaking of which, we can move to the other sorry, I'm reviewing another message that YouTube has sent. It is saying that the bitrate is lower than recommended. Okay. Okay, let's proceed. Let's unbox this piece that we were just talking about. This is the external wiper again. So this one, aha, I see what has been done here. Interesting. Very cool as well. So this one is similar to this one. However, can you notice what is different? So, we were mentioning about how the wall thickness, oops, don't break the new pieces. Okay. We were mentioning about how the wall thickness here was very thin, so it didn't print it, but printed fine because of various slicer settings for different printers and such. Now for this revision, it was printed in a different orientation. Here you can see this print was oriented with the Z going upwards, whereas this print was likely laying down like this and printed with Z going upwards this direction. So Here you can see evidence of that because supports were likely here, and they have been removed and post-processed. So this will be interesting because if we're able to still insert the heat set inserts, which go there on these holes, then perhaps it will still be a usable piece. If it's not usable, then that's okay too. We can always use a piece of tape to cover this. It should be like a very resourceful solution. Okay. So Nerd Garage says, come a long way since the old days of robot parties. Thanks, hopefully, yeah. The stream still looks okay here, but then watching it at a relatively low bit rate too. Yeah, it seems to be the default settings of OBS, so I can review those later and see what improvements can be made for the next stream. For now, it's working. On to the next pieces. Which one should we cover next? These ones? Okay. I'm actually unsure what these pieces here are. Oh, nice. These are very cool pieces that I can't wait to show. Okay, these pieces are the sleeve bearings. So when the external wiper is magnetically coupled to the internal wiper, it revolves about a sleeve bearing. So a sleeve bearing is basically a cylinder within a cylinder. We went with this approach because if we were to use ball bearings, it may increase the likelihood that it could get jammed or corroded. So with sleeve bearings, it's relatively straightforward, and we want to reduce the risk of anything jamming as much as possible. As well, sleeve bearings are much easier to inspect given that they're sort of open and therefore clean as well. So this piece is the sleeve bearing, and this carries a decent amount of the load that is placed on the sleeve bearing. So this is a milled piece. It is so cool and shiny. Yes, that's awesome. So in this piece, there's 5 mounting points for M3 screws. So lots of redundancy there. We can afford to lose 2, maybe even 3, and hopefully it will still work. Okay, so those pieces, as I mentioned, they are sleeve bearings. So let's see where the sleeve pieces are. So here they are. These are made out of Delrin, so as low friction as possible. It's also 1/8 inch, so the surface area is small. Okay, so this is my first time seeing this. This will be really neat. Here's the piece that gets inserted into this, and then it is coupled to this. So the wiggle room, it is evident by eye. It looks to be about 1.5 millimeters. So the two halves of the sleeve bearing are able to press against each other and still rotate because of the low friction of this material. Now, with having an offset of this, something to keep in mind is like how it will handle when it's sort of rotating on its edge, meaning like one portion of it has more load than the other. So this appears to be fine because the outer border of this piece is sufficiently a long enough diameter such that it still rests on the Delrin piece as it rotates, even if it were to have this angle offset. Even if it were fully pressed against the face of this piece, it still rotates very smoothly. So on the detail camera here, I'll switch it over. I'll give a demonstration of it rotating. So here's that piece. And then this goes on top of it. So yes, that rotation is quite smooth. And then there is this piece that sort of couples onto the other side, like this. And then there will be fasteners here. And yeah, that's how that will work. Great. I'm glad to see how well those pieces turned out, given that they're so small. It's nice to see that they were able to turn out well. Okay, so the next piece that would be great to follow that, let's see if I can find it. Here we are. So the next two pieces here are the angle bracket pieces, also 3D printed. Now you might be wondering, why would we 3D print a piece that is going to have so many forces on it with the sleeve bearing? Well, that is because we needed the flexibility of being able to print these pieces just in case there needs to be any fine-tuning in the Z direction in terms of height. So in order to be able to have that flexibility, we went with 3D printing these. Here's here's how that would be assembled with that attaching to that. These prints appear to be incredibly strong. The surface finish on this piece is especially nice because of the angle. It creates a bit of a nice shininess to it. Okay, let's unbox the next piece. This one. I am uncertain what this piece is. This piece is the internal magnet wiper. So the internal magnet wiper is similar to the external magnet wiper, except it's on the inside of the buoy. So this is where the other half of the coupling magnets are located. So on this piece, it's interesting because luckily they 3D printed it in two orientations. One where it's resting on the base and then printed upwards, and then the other one where it was resting on its side. I am curious to see on the close-up camera if we are able to see how the post-processing was done on this piece. Oh, interesting. Okay, very cool. So, yep, here is the internal magnet wiper. Okay, what's next to unbox? Let's try these ones. These are the threaded rods. Amazing. These threaded rods are used when the fasteners required are too long, so going with threaded rods that have been cut. The dimensions of these threaded rods, it is based off of an M6 screw or fastener, so it matches with our existing fasteners for the entire robot. So this set of threaded rods, these are likely for the ballast, and that is evident because it is in sets of 2 plus an additional one. The additional one is likely for the spool holder. Here's another piece, another handle. So this was, looks like it was 1/2 of the handle. So like cut in half. Very cool. So on the topic of the handle again, here are some pieces are also interesting. These are the clamps. So the clamps attach around the buoy. And it basically is what fastens this external mounting structure to the buoy. What's interesting about these pieces is that they're compliant. So they sort of use the way that the 3D printed, they use the way that the 3D printer deposits the material to give it some of the springiness that is observed here. I expected, or I had hypothesized that this material would be less springy than the material that is printed here. It should be regular PLA. However, turns out it is quite similar, actually. So this is interesting. So for example, here is the clamp that is printed here in red, and the one printed at Design Lab in black. Okay, the one printed in black, it does have a tiny bit more resistance than the one printed in red. Here we go. This piece is sorry, scratch that last sentence. There we go. Great, we got the clamps. So here's another set of clamps. And we will see how these differ to those ones, or if they are similar. It appears as though these pieces had a little bit of a bottom layer issue. Apart from that, they look exactly the same. Or would it be top layer issue? Uncertain. Ah, yes, top layer issue. Nonetheless, it's still a usable print. Great, we got two then. Enough for two buoys. Aha, I did not see a few pieces that were relevant to before. This is another external wiper. Woohoo! So this is an external wiper where The result is as desired. Yay! This external wiper has the thin 0.8 millimeter wall, and it's printed in the Z-axis going up. So this is great news because we have this very durable print now, and the holes for the heat set inserts are tidy. Great. Okay, so our collection of pieces here is getting quite tall. Oops. And sort of a landslide a little bit. Okay, I will transfer it to the close-up camera so I can show you the pieces. Nice. So here you can see the latest external wiper that was just unboxed. Pieces everywhere. Alright, now on the stream, what we're going to do is we're going to pause for a little bit of a break, like a 2-minute break, and then we will be back right after that. Okay, we are back on the stream, continuing our unboxing. We're about halfway done now, and there's still more pieces to unbox. What we're going to do is we're going to clear the plate here to make room for some additional pieces. So these pieces will just go into a pile of the open pieces. There's so many pieces. Woohoo! All right, tidy up that pieces, and now there is one more sort of set from that I think would be good to unbox now. Let's move back to here. That noise is just the 3D printer. It is currently printing, and it's near the end of its filament spool. Okay, back to the external wiper again. Once more. Here is another cap and internal magnet piece. So again, the cap and internal magnet piece. Okay. So yeah, that's that. Now let's see if there is anything from the set of metal pieces that is similar to what we have shown already. There is. This is similar to the handle that we showed. So the handle that was shown previously, this was milled out of HDP, and this one is 1/2 inch thick aluminum. So quite a bit sturdier, and it is not sort of warped as this piece is presently. I will move over to the deck cam. So here you can see this HDPE piece, a little bit warped, but the aluminum piece is fine. Great. Awesome. So on to the next pieces then, the last half here. All right, we'll get the biggest ones out of the way. So these are rope guides. The rope guides is what shrouds the spool holder sort of assembly. Remember this is the two pieces that stick out so that it holds the spool of paracord in like this. Well, the rope guide is so that it goes across like this, and then the paracord goes out of there, and so that way it's less chance of it getting tangled. So there's the rope guide. There are 2 rope guides, and these have been fabricated in different orientations for the 3D print. So we'll start off with this one. This rope guide has been 3D printed with Z going up, and it's in the nylon filament. Then there is this rope guide, and I am uncertain regarding the orientation. Perhaps the printer has banding issues or jitter issues, so it's a little bit deceiving. It is it seems to be oriented in the same direction because, as evident by the lower layer, that's where the build platform was. So there's that rope guide, and then also fabricated a rope guide here, and this one is quite a bit more lightweight than this one, and this, so there's that, and then also had a rope guide fabricated out of metal. So this is the aluminum piece and was welded on the sides to attach the 90-degree pieces. Actually, sorry, to correct myself, the 90-degree pieces were already attached. However, the way that this was bent meant that there were slits where it was sort of not joined together to the flat piece. So that's why it was welded. So we have a variety of 3D printed ones and also the metal rope guide. The preference for the rope guide is actually to be a material that doesn't have sharp edges. So for example, if we were to go with the metal rope guide, shoot, I wasn't on the right camera. Sorry about that. All right, if we were to go with the metal rope guide, what would have to be adjusted is adding a bit of a grommet of some sort to the exit hole, so that way the paracord isn't getting sliced when it is moving through. Whereas with the 3D printed ones, those are inherently sort of smoother. This one needs post-processing. That was the one that I printed here. Okay, so we got all the rope guides lined up. That's very cool. Okay, next up, let us unbox this piece. Hopefully I'm on the right camera. Yep, okay. Here's this piece. I am uncertain as to what is underneath this bubble wrap. Ah, yes. So this is the metal piece that attaches from the external wiper to the sleeve bearings in a way. Neat. This is a piece of metal, and it was bent to about 90 degrees here, and this sits inside of the external wiper like this. And we can see how well the cap fits on, and yes, it fits. That's great news. Let's move to the other camera. So here you can see for how the assembly of the external wiper comes together. Now, I am going to momentarily step out of frame so that way I can share on Twitter about the stream being live. Great. Okay. Back to this. And back to that. The camera that is used for this view is just a laptop, so it has to be, the screen angle has to be adjusted in order to get the camera angle properly. Okay, great. So we just unboxed that metal piece with the two 90-degree bends. Now there was also one that is fabricated in aluminum as well, and that is right here. What's interesting to see in the differences of these two pieces, even the one with the weld, is the bend radius. So the bend radius in one of the pieces, the one right here, is quite a bit less than this one. And how this will affect the assembly is dependent on the cap piece and how the cap will sit on the piece like this. So there are fasteners and three fasteners that go through the cap, through the metal piece, and attach onto the external wiper. A closer look is necessary. However, from an initial look right now, it is very evident that this piece is more flat than this piece, meaning the bend radius of this piece is quite a bit significantly more. In terms of height of the mounting holes, this is also an interesting observation because it is a different height. Okay, good. This is something good to keep in mind. Now, the reason why the height difference um, can have an impact on how the whole robot gets assembled is because it attaches to pieces that have to be under tension, sort of like rubber bands. And we'll cover that more once those pieces are unboxed as well. Okay, here's another piece to unbox. See, it's pretty sweet. So this is another piece that we've unboxed, but fabricated in a different way. And this is also GoPro holders. So we really won't lose GoPro with this piece, as long as the fasteners do not come loose. This was milled aluminum. And here are the pieces for the GoPro. So similar to the ones that were printed. Oh, there's one. The reason why there is an offset for this piece is because the nature of the buoy being a Nalgene means that it is not completely symmetrical about the halfway point. That's because it has a lid on it. So that's why it's offset, because we wanted to make sure that the upper stage base was symmetrical, and especially for the mounting points. And so that's why the GoPro pieces ended up being not symmetrical. So here you can see the difference between the milled piece and 3D printed piece. It does not bend. Yay. All right, up next is another piece to unbox. Yes, here are more of the pieces that have the two 90-degree bends that were made out of metal for the external wiper. So these ones were 3D printed, and we could also see how the strength will differ for these pieces. The good news is that the print orientation is the correct direction for the loads that will be on these pieces. With that being said, though, they really do flex quite a bit more. However, it is flexing only in the middle, which will be constrained. So yeah, this would be an interesting test to see when it fails. Not sure if I would want to test it immediately for making something that works for sure. All right, on to the next piece to unbox. Okay, here are gaskets. These gaskets are made out of rubber. So the rubber has been cut to the same pattern of the 90-degree piece, basically the external wiper. So the gasket lays on top of that, and that will form, hopefully, a seal between the magnets and the exterior. Is this necessarily true? It seems that there might be a tiny modification that needs to be done on the gasket piece. And perhaps this is in the assembly as well, where the mistake is. So as it is, the gasket is like this. The gasket is a complete rectangle. Here is the 90-degree piece for reference. So let's show this one better. So then the gasket would be, this would sit on the gasket. And then the cap would sit on this. So that means that the entire pattern is the external wiper, the magnet holder, the gasket, the metal piece, and then this. However, on this review, what would be more logical would be if this gasket had a rectangular cutout such that this goes in between the external wiper and the magnet holder piece. That means that it would be sandwiched between the two and form a seal, a contact seal that would hopefully prevent the magnets from getting submerged in the water. Okay. This will have to be reviewed again in more detail. But it's good to see these gasket pieces. Great. Okay. What is next to unbox? Next up are these two pieces. Sorry, yep, two pieces. Yep, that's correct. These two pieces are mounted onto the upper stage base, and they are what hold the buoy in place. So, if I can somehow get this, there we go. So these are mounted onto here, like that, and it holds the buoy when it is resting. The proper orientation will need to be checked. So, and the buoy just rests like that. Originally in the design, there was supposed to be foam that is placed on here, on those two edges. However, it appears that it's on back order. The fabrication of these, it appears, it is 3D printed and out of the nylon filament as well. You can tell it's a very dense piece. Alright, next up for the unboxing is we will go with these pieces. Actually, no, not those pieces, because there's more that can be explained about that after. Okay. So, next up we'll unbox this piece. I believe these ones are the pillars to the whole robot. Without this, the robot would not have an upper stage and a lower stage. It would be two complete, unattached halves. These are the threaded rods that go between the two stages, thereby attaching the whole robot together. The whole assembly comes together with these pieces. It's interesting in designs when you have those critical pieces that sort of join the whole robot together. Okay, let's compare this with the threaded rods that were also unboxed earlier. Great. Yep, we do have all 6 that are needed. Okay, so here are the threaded rods that go between the 2 stages. So at the beginning of the stream, when I unboxed the stages, there are 6 mounting points on the outer edge of these 2 bases, and then these are the pieces that go in between. So the maximum height distance will be this much. Now, in the design that I sort of modified after these were fabricated, I added some additional rigs to help align the pieces when I'm installing it. So these are 3D printed here, and they basically just sandwich this threaded rod like that. That way I can tell what the distance is in between the 2 stages, so that way the hex nuts are set properly during assembly. Additionally, the way these jigs were designed, or the way I designed these jigs, is that you can attach 2 halves together like this, and sort of enclose it with M3 screws, and then it just makes a nice sort of cover for the threaded rod. So there's unboxing of 2 pieces at once, let's say. Okay. No other comments yet? Feel free to leave a comment if you want. Okay, on to the next thing to be unboxed. So the next thing to be unboxed are these sort of custom washers. These custom washers here are fabricated from Delrin or HDPE. Looks like HDPE. It also looks like the HDPE was faced in order to get this proper width, which is 1/8 inch. So these washers attach on the exterior mounting holes like this, and these washers are there to be a place where the hex nuts can sit. I'm just going to help my 3D printer. There we go. Great. that print has completed. So these washers are basically mounted on each stage on the upper face and on the lower face. So that's why there are quite a few of them that have been fabricated. Now additionally, in addition to these HDPE ones, we also have ones that were made in 1/8 inch aluminum. So this will be interesting because the hex nuts are also metal, so ideally we would probably go with using the aluminum ones to be able to distribute the weight. Either way will be fine. However, the aluminum ones may be less slippery than the HDPE ones for the hex nuts. Now, it's great and all to have these washers to distribute the weight. However, what about vibrations? So we mentioned that there's threaded rods that join the two stages together, and those washers are what are used on the mounting points. But to reduce vibrations, there are these rubber pieces. The rubber pieces are sandwiched between the bases and the washers. So that way, less vibrations are traveling through the entire threaded rod. So these rubber pieces that we just unboxed, they sit like that, and they will be sandwiched in between the washer and then the hex nut. On the lower stage, they are even included between the lower stage and the stands. So yeah, they are kind of a very important piece, and there are plenty of them, it appears, in here, which is good news. The durometer of the rubber is medium soft, so it's not too soft such that the washer would just sink into it, and it's not extremely hard such that it would just transfer the vibrations. So it's sort of medium. It can be depressed right now by squeezing it in between my two fingertips. Okay, so we covered that. Now what's next is, let's dive into how the external wiper attaches to the sleeve bearing. Alright, so that's these two pieces right here, and they also look like rubber gaskets. Now there's multiples created of these pieces, and that's because we don't know exactly the height, because it depends on the tension that we will want to dial in. So these pieces right now, I am stretching this one, and this is basically what attaches from the metal piece, and then it goes to the other white piece right here that's on the sleeve bearing. So this forms sort of an elastic band effect for the external wiper to sort of stay attached to the buoy. Even though it's already magnetically coupled, this just adds a sort of mechanical aspect to keeping it attached. So we have quite a few of these pieces of different lengths, so that way we can choose which one provides the amount of tension that is desired. As well, it appears we have multiple sets rather than just one. So that is great news to be able to experiment with. And it appears that this is the same for this set as well. Perhaps it is a little bit of a different durometer using. This will have to be investigated further. nonetheless, there is certainly enough to be able to choose which length we want for both sides. The reason why both sides will have a different length is, again, because of the symmetry issue of this type of buoy enclosure that we chose. And we chose this because it's more accessible. It is also ended up being less expensive than, say, an acrylic tube of the same dimensions. Additionally, with this, there's only one exit location that has to be sealed. So for those pieces, the rubber pieces, they're held in place also as a sandwich with the M6 screws and this clasp piece. So this clasp piece here is fabricated out of Delrin, it seems. And the reason for going with Delrin is because we were unsure if the aluminum would end up cutting into the rubber. So that's why we went with this. That being said, probably going with aluminum would have been fine anyway. However, I completely forgot to add that onto the list of pieces to be fabricated out of metal. So they're made out of Delrin, which is fine too, and we'll be able to test it. Now, I just finished mentioning about the buoy enclosure and sealing it. So that brings us to the O-ring pieces. The O-ring pieces are pieces where the rubber band-like piece sits in a group and it forms a seal. So here is this piece. This is the O-ring piece, and the features of this is that on the bottom there is locations for heat set inserts, and that will then attach to a bracket that mounts the circuit board, which I can show here. So this is the bracket which then mounts the circuit board, so that attaches in like this. Now this is like one of the key improvements from last year, because last year in our version 1 of the robot, everything was attached to the lid of the Nalgene. However, this was problematic because the lid is sealed onto the Nalgene through threads, so you screw it on by rotating it. However, there was no predetermined start and stop location of this, so that meant that you could have, say, stickers blocking the way of the wiper or the camera, let's say, if you had one in there. So this means that with the electronics mounted to it, we get to determine the orientation as indicated by this arrow. So here is the groove where the O-ring sits. Now this groove, because the O-ring piece here was 3D printed, this groove is actually, let's see, would you call it a circular profile? Yes, a circular profile rather than a rectangular profile. Now, the reason why this I went with a circular profile rather than a rectangular profile was simply because in the common manual for O-ring design and choosing which sort of O-ring you would want to choose, it was unclear to me because of the date of when this manual was written, if circular profiles were excluded because of 3D printing not being a common manufacturing method back then. So because O-ring pieces were likely to be milled back then, it would be a rectangular profile. a slot. So went with this approach where the O-ring just fits inside of this. Now, this may be a detriment because it's possible that it means that because it fits perfectly with the O-ring, it means that it may not have space to expand onto that contact face that is on the O-ring piece. So, yeah, that may be the case for this type of piece. So, basically, if it were to be a rectangular profile, it's possible that it could expand a bit more. Now, the expansion of the O-rings themselves happen under pressure. So, here's an example of the piece that was printed here, and this was iterated on multiple times. There are some details to this piece. So there is basically texture in these pockets, and that's so that you can get better grip with pliers to pull this out. Additionally, there is a circular hole cut out in between this blocker piece here, and that's so that you can thread a piece of string through it if you want to dip this into Plasti-Dip to completely seal it. That is, of course, a risk of 3D printing O-ring pieces, and that is that you're uncertain if it's completely watertight. The water could travel in between the layers, get into the infill, and then travel out the other layers. This is something that will have to be tested, and as well testing with Plasti-Dip to see how well it seals it and to see how well that holds up when you're adding the O-ring around the Plasti-Dip. Will the Plasti-Dip adhere well to the plastic? That will remain to be an unknown until we test it. So here's an example of a previous iteration where I was testing a double O-ring design, which provided too much friction to be able to remove it easily. So here you can see the rib was actually bent because of the force when trying to remove this piece. And this I'll probably use for testing for Plasti-Dip. Here you can see the earlier iteration A4, which was the single O-ring piece, but without the cutout for the thread or the string for the Plasti-Dip. But all of these iterations are still useful because I want to test it. And here's even A3. Now in terms of mass, so here's the A5 printed in nylon and the A5 printed in PLA here. It appears we use similar slicer settings in terms of infill at least, and outlines too. So the difference in weight will likely be quite minimal. Watch, I say that, and probably in quantifying it, will probably be quite different. Okay, so that can go back into its baggie until we are ready with it. Okay, and then there are additionally other O-ring pieces. So here are the other O-ring pieces. There are two more that were printed. And they appear to be quite similar. So here's one more. This is great because there are 3 of them. It means that we can test with some Plasti-Dip on these as well. As well, we could make buoy kits to send to the collaborators. This one is fine as well. Maybe a little bit of on adhesion from the build platform, but it's fine. Great, I'm so glad that these pieces turned out well. Actually, this one is still the circular profile. Yes, okay. The next step for the O-ring pieces would be to have them milled from a solid piece of plastic and have the threads where the heat set inserts would be actually tapped. So Design Lab looks like they included some O-rings as well. So now we have plenty of O-rings. Great. Yeah, thumbs up. It's funny because like we already have 200. Now we have 210. All right, now we're on to the almost final pieces. Actually, let's stick a little bit with the internal pieces. So the O-ring is sort of internal to the buoy, and then there's a few additional pieces that are also internal to the buoy, and that is the holder piece for the internal wiper. So last year, the internal wiper was fabricated using 3D printing, and it was astounding to see the amount of force that that piece went through, because it was not only the torque from the servo motor acting on it, but also the resistance force from the coupled magnets to the external wiper. So last year, the 3D printed piece ended up snapping multiple times with 2 different prints. The problem is that because it has to be so thin, the 3D prints were quite weak, and it ended up just being hot glued. So now these are fabricated out of aluminum, and it's 1/8 inch thick, which will do just fine. And so the servo gets mounted directly onto here with its circular servo horn. So that means that there's at least 4 mounting points. And these pieces were also the 90-degree bend and the aluminum weld. So there are 5 versions of this piece because the height has to be fine-tuned. Sorry, not the height, the offset from the servo motor to the exterior wall. So, for example, if you were to look through the Nalgene and then you put this into the Nalgene, basically this distance from the center point of the servo rotation to this face here, this has to be fine-tuned such that it's like relatively close to the internal face of the Nalgene. Now, this is easier said than done because it not only relies on that, but it also relies on the assembly process. So the internal wipers, when they are assembled, they go into the Nalgene in a process where it's sort of like a jigsaw puzzle. The servo is mounted onto this wiper, but it has to be inserted before the rest of the electronics. And we'll dive into that more on the other pieces. So in order to properly index these 5 pieces, there is a slot and a slot with a circle, so that way these are identified and it can be matched to the CAD drawings to determine exactly what is the correct offset. And it is pretty amazing with these pieces to just be able to see how well the bend turned out. Okay, next up, I mentioned about the servo mounting to the internal wiper. So that's what these final pieces, let's double check that they're the final pieces. Okay, yeah, the second final pieces. That's what these second final pieces are about. These are all of the pieces for the servo module assembly. So the servo module assembly is the smallest assembly of the entire robot. In fact, it uses M2 fasteners in the assembly and even M2 heat sets. So the servo gets mounted into the servo mounting plate, which is 3D printed here. And there is also a helper piece, which I designed to hopefully save my sanity. So this helper piece, I'll transfer to the correct camera. Okay. This helper piece right here will attach on the opposite side of the servo horn, and it can house the hex nuts. So the premise of this is that I can use it to assist with assembly, whereby I can just insert the hex nuts here, maybe add a little bit of glue if they don't stick properly, and then attach in the fasteners through there, and then to here. I believe for the fasteners on this side, they were actually special low profile head fasteners that I selected because I want the internal wiper to be as close to the bottom as possible, but without touching it. And we needed to be able to maximize the amount of space for the circuit board, so like every spare millimeter counted, especially with the extra space that the servo module assembly took up, which you'll now see. Okay, so you saw the piece that the servo mounts to. Now it's time for the next piece, which is here. So this piece attaches on to the servo mounting plate. This piece attaches onto the servo mounting plate, and it will house 4 M3 heat sets. And then up top here, it will house 2 magnets, and there is also, yes, it houses 2 magnets here, and then there's also another piece that closes off these magnets, and that means that it needs to attach, so then there's 4 M2 heat set inserts here, and then the M2 fasteners that attach that down to keep those magnets protected. And so those magnets then attach to another piece. I'll just unbox this one, but this one isn't next. That's not next. There's a different one that is next. Okay, this one is also not next. Okay, here we go. This is the one that is next. Also, these are labeled for easier understanding because I knew it was going to be slightly confusing with these sort of jigsaw pieces. So the servo mounting plate is named A1, and then this one is A2. So then you have to look for, 3A. So 3A mounts on top of this one. so it closes off access to those magnets. And then it has a key piece here. And the key piece mounts to 4A. So 4A has location for 2 magnets as well, and so those get inserted this way. And then there is, I believe it is, yep, 5A. So 5A gets mounted like this. So 5A has housing for 4 M2 heat set inserts. So both of these 2 pieces are assembled at different times. So this one still needs to have its magnets closed off, so it gets assembled like this. No, it gets assembled like this, so then these 2 are attached like that, and then this means that it can be keyed together like this. And then this piece here, this 90-degree tab, is actually what attaches then to the circuit board holder bracket. So there are a variety of pieces for the servo module. I thought I almost lost them for a second. And it looks like they have been printed in different orientations. So this is good news because it appears as though on some of these, like this one there, is still supports in the magnet holders, but on other pieces it looks clean. Here are the variety of pieces. So this is going to be really great to test. I was uncertain regarding how the tolerances will be, because everything is so tiny with the M2 screws and the M2 heat set inserts. Now there are also additional pieces that also look like they are servo module pieces. I am unsure why they are in their own separate little compartment. Perhaps these were printed in PLA or something. Interesting. Well, anyway, yeah, there are now extra pieces of those. Okay, that is the unboxing of all of those pieces. Woohoo! There's still a few additional pieces, so don't tune out yet for all of the viewers out there watching this amazing stuff. All right, so the next pieces to be unboxed are going to be these, and these are the DIY bungee cords, because the bungee cords that I want to attach from the deck stage to the upper stage where the handles are, that distance when measured in CAD was 4 inches, and it turned out that finding bungee cords for 4 inches was quite challenging. Didn't want to go the route of like running a bungee cord over the top of the robot, so decided to get this cord, this stretchy DIY bungee cord, and that will be fed through these bungee cord hooks, and then attached to these sort of um, metal fastener pieces that are like semicircle, and then to the handle. So there are I believe there are 8 of these. Yes, there are 8 of these bungee cord hooks, and so there will be 4 bungee cords because there are 4 corners with that fastener mount that will be there. Okay, so these pieces, as they were printed on my 3D printer here, they are going to need some post-processing. And then, of course, assembling with the bungee cord. Okay, what's up next to unbox? So everything is complete from the 3D printed pieces here. We have seen everything now. For that, here's yet another internal magnet holder piece. This one was printed to test to make sure that the small ridges were sufficient to not have the supports touch the exterior, the face of the buoy. It worked fine. Okay, so the next and the final piece for tonight's unboxing are the ballasts. So here are the ballast pieces. These are a combination of different material thicknesses. So here is a ballast piece that is 1.5 inch thick, and then down to 1/4 inch, and then down to 1/8 inch. So the objective with the ballast is twofold. The first one is to distribute the center of mass so that it's located near the center of the robot. Because this robot is descending to the seafloor and we want it to land upright in order to reduce risk of the buoy not launching, we really want it to land upright. In order to do that passively, one way we could do that is by making sure the center of mass is located in the middle of the robot. So that means that the location of these ballasts were placed in CAD and then checked for like how far the center of mass moved. Then for ballast there is the amount. So the amount has to do with the weight of these. The buoyancy force is dictated by the amount of volume that the volume of water that the robot displaces. In order to overcome the buoyancy force, because we actually want the robot to sink, we need to make sure that the entire weight force of the robot is more than the buoyancy force. I actually made a physics model to calculate this, and the result is that the robot has to be greater than 6 kilograms in order for this to have weight to buoyancy ratio greater than 1, meaning that it would sink. So these ballasts get mounted onto the lower stage where those funky looking mounting points were. And as well, that's also why there are these threaded rods. So these can be inserted through this, and then the exact height can be tuned in with, I think we have wing nuts available, which is handy. So time will tell once we start to assemble this if this is enough ballast. Okay, that concludes the unboxing of the EJA version 2 pieces. It's so great to actually see all of the pieces here in person, and actually hold the work of the design. So the design went through so many iterations for all these various sub-assemblies. Uh, uh, there were like weeks where I would design something and then see a different or a better way of doing something, and then ended up just scrapping it, starting over, and then making the design again. So all of the pieces that you see here are basically a testament to arriving at that final workable design, and then I can build from there based off of the results that we see. The results that we see would be from testing in the field and then also testing with the user. So we have two sort of metrics that we want to evaluate here. There's the how it functions in the field, how it holds up, and then how it operates, how the user interacts with it. So off the bat, I already have superstitions about how the user interaction will go with this spool holder, because one of the ways that you evaluate the effectiveness of ropeless fishing systems when they're in use by fishers is seeing how fast the reload time is. So in our case, that would mean respooling this paracord onto back and then resetting the buoy in place. So yeah, that is basically a summary of that, and the next steps are to now assemble the robot and document the process. The process is all documented on the hackaday.io page. I'll update the description to include the link to our page. And on that page, you can find the electronics progress as well. And this has been a part of the Hackaday Dream Team's initiative. So what this means is that it's all been developed as open source, with the hope that it will be able to impact as many fishers as possible who would be interested in implementing this as a solution. There's been some news from NOAA recently, NOAA meaning N-O-A-A, and that is that ropeless fishing gear is now allowed on the East Coast for some regions on October 18th. So that's great news for being able to take the first steps to implementing this technology in the field. All right, well, that's probably enough of talking for now. Feel free to leave a comment with any thoughts. The next live stream will likely either be about assembling this, so possibly not as much talking, but leaving the stream up and just assembling, or it could also be about assembling the electronics, which also has to be assembled. Great. Thanks for the 3 people who tuned in. That's awesome. I'm sure people will watch it too. Yeah, totally sure. Yeah. Okay. Okay. Thanks, everyone, and see you next time.